This is Calculus 1, Section 2.0 lecture, and this is all about sketching derivatives. And so before we start, I want to make sure everybody knows what a derivative is. So in Section 1.0, I talked about how about the tangent line, and that like using the idea of a secant line, the idea of if the secant line is going through 2 points, if one of those points gets closer and closer to like the first point, then we have what's called the tangent line. And the derivative is the name that we use for the slope of the tangent line. You can also think of the derivative as like the slope of the curve. It's kind of like if you think of slope as representing, just intuitively think of slope as meaning steepness of a line or steepness of a curve. You can think of the derivative as the slope of the curve also. And then just like if you're dealing with a function that represents some situation in the world, then the derivative represents instantaneous rate of change. And specifically, if you're talking about like a position function, like a function that represents the location of some object, then the derivative represents instantaneous velocity. So derivative represents all these things that I wrote down here. All of this is the derivative. And again, the derivative it's really just the slope of the tangent line. And you can do a lot of stuff with the derivative. Like if you have a function that represents a situation, then the derivative will always represent the instantaneous rate of change. But then you can also do a bunch of other stuff with the derivative. Like you can, if you have like the derivative of a function, you can actually get information about the function, like really important information, like where the function has like maximum points and minimum points, where the function's increasing, where the function's decreasing. Now, look, this doesn't sound all that exciting right now because we have graphing apps, we have Desmos that we can just put the function in and get all that information just by looking at Desmos. But just imagine in the 1700s, like you could use the derivative to like get information, like all the important information about a function, without having to graph the function. Just using the derivative, you can do it by hand. Also using the derivative, you can actually calculate like solutions, will estimate solutions to equations that you might not know how to solve. So there are various uses for the derivative, and this semester we're going to spend most of the semester talking about derivatives. So all of chapter 2 is really about finding derivatives. Derivative that, derivative this, find this derivative, find that derivative. It's like just finding derivatives all of chapter 2. And what this section is about is using the idea of sketching a derivative to get an idea of what each function's derivative looks like. So throughout chapter 2, we're going to be learning rules, rules for finding derivatives of various functions, and just to get like an intuitive idea of why these rules are true, it's helpful to be able to sketch a derivative of a function if you have the graph of a function. So that's what this section's about. So I'm going to just, before we start this, I'm going to take us back a little bit to some algebra. And just a reminder about algebra, or just from algebra, that if you have a line, right? If you have an increasing line, like the line that I drew on the left here, the slope is always going to be positive. That's because when we typically, when we read graphs in mathematics, we read from left to right. And to go from the point on the left to the point on the right, we have to go up a certain amount. So that's our rise. And since we have to go up a certain amount to get to that point, the rise is positive. And then we also have to go over a certain amount. And since we have to go over like to the right, the run is also positive. And slope is defined as rise over run. And so our slope, if we have an increasing line, is a positive number divided by a positive number, which is positive, which means that our slope is positive whenever we have an increasing line. If we have a decreasing line, on the other hand, to get from one point to the next, again, reading from left to right, we actually have to go down. This is the line in the middle, which means that our rise is negative, and then we go to the right and our run is positive. And so rise over run in this case would be negative over positive, which is a negative number, which means our slope, whenever we have a decreasing line, our slope is negative. And then last of all, the other type of line I just wanted to look at is the line on the right, and that's a horizontal line. And with horizontal lines, the slope is always going to be 0, because once again, slope is equal to rise over run. And if you don't have any rise, you just have 0. So like a horizontal line doesn't have a rise. Like it doesn't go up at all. It doesn't go down at all. It just stays. Run is whatever, but anything 0 divided by anything, as long as it's not 0, 0 divided by any number besides 0 is just going to be 0. And so horizontal lines in general have slopes of 0. So I'm going to go ahead and take a moment. We'll do an example. So just using this, actually, you know, one other thing I want to talk about before I write out an example. One other thing I just want to point out. If you have, I'm going to draw a curve. So let's say I have this curve here, right? And notice, so like I was saying earlier, when we read graphs in mathematics, we typically read from left to right. So I'm going to start reading this curve from left to right. And what I want you to just notice about this curve is that on the left side of this curve, the curve is increasing. So I'm going to I'm just going to plot some points on this curve. Just points where the curve is increasing. So notice the points that I just marked. Notice the curve is increasing there. If we're reading from left to right, it's like if we were to be walking up this curve, we'd be walking uphill. And I'm going to draw some tangent lines at these points. So here's a tangent line. Here's another, sort of. Okay, that's not the greatest tangent line here. I'll try again. Here's another tangent line, and then I'm just going to draw another tangent line to this curve. And notice what I want you to notice here is that all the tangent lines to this curve that I drew them on the part of the curve where the curve is increasing. And notice all the tangent lines are also increasing. Which means that since the tangent lines are increasing, their slope is positive. So their slopes are positive, I should say. All of their slopes are positive. And so just in general, this is just a general rule that if a function is increasing, what that means is that its derivative, because the derivative is the slope of the tangent line, And the tangent line will also be increasing. So that means the derivative is positive. And now I'm going to draw some tangent lines on the other side of the curve where the curve is decreasing. So these points that I'm marking in green, notice at these points, the curve is decreasing. And notice the tangent lines that I draw are also decreasing at these points. At least trying to draw these tangent lines that I'm trying to draw. By the way, so remember tangent lines, this is from 1.0. The idea is that they kind of just like touch the curve at that point. Although they can touch the curve at other points in some situations. The idea is that at that point you see the line touching the curve and then kind of going off in its own direction. So tangent comes from a Latin word that means touch. And so that's the idea. These tangent lines touch the curve. But notice my green tangent lines, they're all decreasing, which means that all of their slopes are negative. And that's just another little rule that whenever you have a function that's decreasing, or whenever your function is decreasing, the derivative, which represents the slope of the tangent line, is going to be negative. And then one other rule I just want to note is that if I take, I'm going to actually get rid of all these, or some of these tangent lines I'll try getting rid of, just so we can get a better view of what I'm about to draw. If I had noticed the peak of this curve, like the maximum point, or if this is a parabola, the vertex, notice the tangent line here is actually a horizontal line. Well, I'm trying to draw. Here, let me try drawing it again. There. This is horizontal. And so just in general, like whenever you have like a curve where you have like a smooth maximum point or a smooth minimum point, then you're going to have a horizontal tangent line, which means that the derivative here is equal to 0. Because again, derivative is slope of a tangent line, and whenever you have a horizontal line, that means the slope is 0. So you can have other situations like this, like you could have a curve going like this, and still you would have like at this point, at the low point, you have a horizontal tangent line. I just have a hard time making it look horizontal, that's all. But the idea is that it's horizontal. So so in general, if you have like a high point or a low point, you'll have a horizontal tangent line, except that at certain situations. So not here. So like if you have like a sharp high point, a sharp low point, something like this, right? Or trying to make a V, or if you have like something like this, like a sharp high or low point, these tangent lines are not horizontal here. Like, and we'll actually talk about this in chapter, I don't know when we'll talk about this, but we will talk about this at some point. Yeah, chapter 3. So we'll talk about this later. But for now, we're just going to be dealing with like smooth curves, smooth transitions from a curve increasing to decreasing, or decreasing to increasing. And that point, that high point or that low point, we have a horizontal tangent line, which means the derivative is going to be 0 right there. So now I'm just going to take a moment and write up an example. So here's an example. Given the graph of y equals f of x, so that's the red graph that I drew, sketch the graph of its derivative. And we're going to use what I just talked about to do that. And over here in purple on the left side of the screen, I just wrote like that. Oops, didn't mean to do this. Didn't mean to do that. What I wrote, like I just mean right here. What I wrote is that just for notation purposes, you know, we have notation for everything in mathematics, like practically everything, symbols to represent everything. And this right here, this F with the parenthesis, sorry, with the apostrophe and then the X, that is the notation that we use for derivative. And the way that you read this is F prime of X. F prime of X. So that represents derivative. So I'm about to draw the derivative function using the information that we just talked about like slopes of tangent lines and so on. So I'm going to write out steps that you want to follow to sketch a derivative. And this is just going to be a general sketch. It's not like any sort of detailed sketch. The idea of this is just to be able to like see a function and then kind of have an idea of what the shape of its derivative is going to be. So that's all. This is, so the first thing that you're gonna do is look for where the tangent lines are horizontal. Look for where you have horizontal tangent lines. So that means you're basically going to be looking for like the high and the low points on the curve. So you're going to find the points where the tangent line are horizontal. So again, what that means is that you're looking for the high points and the low points, the maximum points and like the minimum points that you see on the curve, like the top of the hill, the bottom of the valley, stuff like that. So like right here. Oh, you know what? I want to use a different color. I want to use the same colors I used here. So I used purple. So I'm going to use purple here too. So I have a horizontal tangent line here. And then also I noticed that I have a horizontal tangent line here. Top of the curve, I mean, peaks and valleys basically. And that's where I'll have horizontal tangent lines, which means, so once you find the points where the tangent lines are horizontal, here, your derivative curve is equal to 0. So let me actually use the notation that I just wrote down earlier. So F prime of X equals 0. F prime of X, again, that represents the derivative. So I'm just going to go down to this curve down below. This is going to be our derivative curve. And I get to mark zeros here, like in the same location for, well, the same X value. I have zeros right there. So wherever you have horizontal tangent line, that means your derivative function is going to be 0. And the derivative function, I'm just graphing that directly below. So below the main function. So once you've marked your zeros, that's like your first step. Do that first. I strongly recommend that you do that first. Once you've done that, then you're going to use the information that I talked about earlier to determine where your derivative, so this F prime of X, is positive and negative. And positive means above the x-axis, negative means below the x-axis. So notice what I put here in blue. Whenever my function itself is increasing, that means the derivative is positive. So right here where I say determine where your derivative is positive and negative, this means that f of x is increasing for the positive. And then what color did I use for decreasing? So function's decreasing when your derivative's negative. So right here, that means I'm looking for where my function is decreasing. So that's what I'm doing. So when my function's decreasing, that means my derivative did I say, I don't know what I just said. When my function is increasing, that means my derivative is above the x-axis. And when my function is decreasing, my derivative is below the x-axis. So I'm going to go ahead and look at where my function's increasing. My function, so again, remember, read your graph from left to right. So imagine walking on the graph, like you're walking on the graph from left to right. And notice, starting on the left, I'm going uphill. So I start off with the function increasing. And then once I get over to the top of the hill, then I go down, decreasing. I'm going down the hill. And then I get to the valley, and then I start increasing again. So basically, my graph, of my derivatives, when my curve is, when my curve, my initial curve is increasing, my derivative, or the graph of my derivative, is going to be above the x-axis. That's what it means for a function to be positive, right? Graphically, that means it's above the x-axis. So I'm going to draw just a curve above the x-axis to the left of that point where I have like the top of the hill. So I just drew like something to the left of that above the x-axis. And I make sure, like, you know, those 2 points that I marked in purple on the x-axis where I had my derivative equals 0, I have to go through those points. So that's why I made sure that that little blue, whatever I just drew, I made sure that it's touching that point. After that, my function's decreasing. So like between these 2 points here, I need my function, I need my derivative to be below the x-axis. So it has to be below the x-axis. I know it has to come up at some point because it has to hit that other purple point. And then after that, then my graph is increasing, which means my derivative is positive. So yay, and I'm done. That's my derivative function. This right here represents, this is f, this is y equals f prime of x, like this entire graph. Let's look at homework. So homework's actually faster because it's just kind of like multiple choice. So it says, so like problem number 1, it gives you this curve, the red curve, and it says the graph of the slopes of the red function has which color. So it's asking you for the graph of the derivative, because the slopes of the red function, the slopes of the curve, that's just the same thing as the derivative. So you want to go through what we just went through, which is first, I'm gonna first identify like where you have like high points and low points on this red curve, and it's kind of hard to see, but it looks like we have like a kind of like a low point like right here, and then it looks like we have like a high point kind of like here. And so if I like just go down to the x-axis, because wherever I have a high point and a low point, that's where I'm going to have my 0 for my derivative. I noticed that it looks like I have zeros kind of like right here. They kind of match up, right? So that kind of tells me that my graph is going to have to be either the yellow graph, or I guess they call it orange. It's the orange graph, or the black graph, because the orange graph and the black graph are the only graphs that hit the x-axis, like at the low point and the high points for this curve. High points are kind of, the high and low points are kind of hard to see with these curves, but oh well. So from there, I want to just like notice my curve and just like imagine like going along this curve, the red curve. So you start off, you're going down, right? Down the curve, down. The curve is decreasing. which means the derivative has to be below the x-axis. Like when the curve is decreasing, below the x-axis. And that happens with the black curve here. Like notice it's below the x-axis. And then if I keep going, I'm kind of going uphill a little bit now, right? So my curve is increasing right there, which means that the derivative is going to be above the x-axis right there. If my curve is increasing, derivative's above the x-axis, which again is happening with the black curve. And then I'm going to keep going along my red curve and I start going downhill again, which means my function's decreasing, which means my derivative is negative, which means it's below the x-axis, which again is the black curve. So my answer, I'm going to go with black. My answer, it looks like the black curve is the one that matches, or that is the derivative of this function. Let's look at the next one. So problem number 2. Once again, I'm gonna just make note of where I have like a high point on my red curve. And in this case, I have a high point like right around here. Oof, I had to make that point really big. And notice that that seems to correspond to where the blue line crosses the x-axis. And it looks like the blue line is the only line that crosses the x-axis at the same x value where my red curve has a high point. So it looks like I'm done. Like my answer is just blue. But let's just like look at the other parts of the curve just to kind of reinforce those ideas about increasing curve positive derivative. So notice as I read my curve from left to right, I'm going uphill. I'm trying to go uphill. Trying, which means my derivative has to be positive, which means above the x-axis. And notice this blue line here is in fact above the x-axis. And then after I hit the top, then I start to go down the hill. And that means that my derivative has to be negative, which means below the x-axis. And my blue line definitely is the line. So let's see, blue. I want to just notice something. So you know how I was saying earlier how like the idea of sketching a derivative, it helps us kind of get an intuitive idea about the rules for derivatives of certain functions. And notice the red curve in this example, it looks like a quadratic curve, right? Like it has a degree of 2. And then notice that the derivative function is a line. So it turns out that all quadratic functions derivatives are actually linear. They're actually lines. So like that's actually one of the rules that we'll talk about next week. Let's just get one more similar question just to have another example. Number 1, like these are like really kind of, I don't like them because it's hard to see. Like what's the top? Like where's the high point? Maybe like there's and I'm kind of basing this off of what I see in terms of possible derivatives, but it looks like maybe there's a high point where I just marked and a low point like maybe around here where I'm marking. You can barely see it, but it sort of looks like the graph is going down. Like it kind of looks like the graph's going down, like right here. Like it's starting kind of a little bit higher and then going down. It's actually hard for me. I can't really see it, but I'm just saying that because I know one of these has to be the answer. And I mean, sort of see it going down. The reason I'm just looking for it going down is that I'm just noticing that it looks like my I have like there are like these 2 points right here where the possible derivative curves cross the x-axis. So, and it does sort of look like between those 2 points, the red curve is going down slightly. So I know that my answer is either going to be the blue curve or the green curve. And then if I like just trace along the red curve, notice reading from left to right, first I'm going up, which means my curve is increasing, which means my derivative is above the x-axis. That's happening with this blue curve. Look, it's above the x-axis. And then if I keep going, it kind of looks like I start to go downhill just a little bit. It's a really, really not a steep hill at that moment. And right there, notice just a little bit. The blue curve is a little bit below the x-axis, which means it's negative, which means the original function is like decreasing right there, right? And then now we go back to increasing, going up, uphill. And look at the blue curve is above the x-axis right there. So I'm going to go with blue as my answer for this one. If I can get to it. Oops, not black, but blue. And there we are. So try those. And again, like notice this is actually the red curve. It looks like a function that has a degree of 3. And notice the derivative curve is a quadratic function. It's a parabola, right? And it turns out that a function of degree 3 will always have a derivative that's a parabola. That's a quadratic function. So again, that's another one of those rules we'll start looking at in the next section. Well, in section 2.2, actually. Take care, everybody. Bye.